Hello programmers, welcome to tutorial 4 of my Coder's Basilisk tutorial series. In this episode we're going to be talking about the differences and similarities Coder's Basilisk has to C. And we're going to start with the similarities. The first major similarity, okay, hold on, I'm setting things up so I can see things. There we go, I got the light on. The very first similarity we need to talk about is that overall the abstract machine, quote unquote, works the same, right? This is a little demo program I've written here, but if you go through our, okay, hold on. If you go through our demo programs, right, you can see a very C-like structure, right? Includes, functions, you'll see global variables, you'll see pointers, you'll see inline functions, and you'll see arrays, right? And by the way, notice that the array syntax is a little bit different here. We're going to talk about that later, but things are fairly C-like in structure, in form, right? You even have indexing pointers and stuff, right? We have character literals, we have string literals, all that, so things are pretty C-like, right? Another similarity is we have pointers, casting, and promotion semantics are mostly the same, right? If you promote a 32-bit signed integer to a 64-bit signed integer, it'll do a sign extension. If you promote an unsigned 32-bit integer to a 64-bit signed integer, it will not do sign extension. Basic things like that, right? At least I think I have that right. Let me just verify that really quick. Let's look at the code, right? This is the code validator, which handles hold on. This is but anyway, I'm pretty sure that the casting semantics are more or less the same, right? I guess I don't really need to look up the code to verify that right now. I'm pretty sure I have it implemented that way, right? Actually, no, we can look at it. I just want to show you guys where it's type to promote. Right? Here is the type promotion things, right? Promoted type promote, right? Basically what this does is it takes the promotions takes two types, right, that are arguments to something, right, and then it figures out what the resulting type will be. Here it is, right? If the promoted base type is unsigned and the weaker base type is signed, we increment, which means we become signed, right? So unsigned will be promote to signed, right? I see. I see. Right. The promoted, if the weaker base type is yeah, right. So the promotion semantics are basically the same as C, right? This is the promotion semantics right here. It's just based on this ordering, right? So that's how that works. But there are a lot of differences between Coder's Basilisk and C, right? The first major difference you'll see is that the syntax is generally written differently, right? While things are somewhat C-like in their structure, the actual way they're written is quite different. For instance, we don't put the return type at the beginning. We put it at the end. Dash arrow and then a return type, colon, and then the code. And that's how we write it, right? And you'll see this, you should be able to figure out how to produce almost everything that you usually want to do in C using the examples I've given, right? You should be able to figure out how the basic syntax differs, right? And to help you with that, I've written this little program here that shows, for instance, how if, elif, else works, right? Intriguingly enough, these are never initialized, so the else clause is what it'll actually run here. At least it should, right? Let's see. Let's verify that. 6. Yes, 6 prints out. Actually, need to. There. Anyways, sorry, I was just noticing a weird thing right there. The number 6 prints out, right? So you should be able to figure out the differences in basic syntax, and I'm gonna scroll through this program really quick, and you guys can just see some of the differences. For instance, here's a difference. We put arrays as part of the type. Array does not go here. The array length, it goes here. You also can't have multi-dimensional arrays. This will not compile. That's actually one of the things I mentioned in that list. I see it'll complain to you that no identifier is there, right? And the reason is that you have a square bracket there, right? And now it'll compile. Yeah. We can declare structs this way, right? I believe you can actually omit the semicolons here. You can have semicolons or you can not have semicolons in struct. We also have class as an alias or struct, right? I'm going to talk about the aliases later. A whole bunch of these things are specifically to illustrate the fact that there's a ton of aliases for common keywords, right? Like fn and func. I could change some of these to jump. Jump is a keyword, by the way. Actually, that's... Yeah, okay. And then, you can see that if is written differently. You can see, okay, well, this is metaprogramming. Ignore that. This is just so I can print to the screen, and this is a convenient syntax I wrote. I can show you where that's implemented and how that works, but we'll do that in a different episode when I talk about metaprogramming in depth. There's also this new operator here. We're going to talk about that. And you can see that there's like weird types like awkward. This is just an unsigned 64-bit integer. You can call functions without parentheses. That's a pretty weird thing, right? You can also, on occasion, omit, semicolons from statements. You might be able to notice that. For instance, if I surround this with an if statement, right, I'll now be able to omit the semicolon. This will work just the same. Yeah, see, and now it's... Yeah, so see, we were able to omit the semicolon from here, right? We could then add a semicolon and then do... we could do 3D. Actually, no, we would have to do... Okay, let me think about this. Int a if 1 and a equals 3 plus 5 plus 7. Print int. I'm just showing you that I can omit a semicolon from a statement. And the reason I'm able to do this is because there's an end here, right? So this is another... So 15 right here. I believe this is 8 plus 7. Yes, is 15. Yes. So this is that value being printed out. We can just verify that by multiplying it by 10. By the way, I believe I should add that, right? I do not believe the semantics of the operator precedents are quite the same as C. You can look at the operator precedents in the parser source code, but in general, if you ever want to disambiguate something, yeah, 150. Yeah. See, this statement runs even though it doesn't have a semicolon after it. So that's that, right? So basically, that's that point, right? Basic syntax is a little bit different, right? But you should be able to figure out from my examples and from this code base in particular, from this example here, which will be linked to in the description. I'm going to push it to Git at the end of this video. You should be able to figure out how to do basic C stuff in Coder's Basilisk just from analyzing the examples I've written. The linked list example, the hello world example, the multi-threaded example from the previous episode, episode 3.5, and this example. The second thing we need to talk about is that there are lots of aliases for keywords, right? And the way I'm going to show this to you, right, is I'm going to show you how the parser actually parses keywords, right? What it does is it first classifies all tokens as identifiers, right, that are in the identifier form. Then it goes through the identifiers and it checks if it's one of these identifiers. And if it is, then it sets it to be a keyword instead of an identifier, right? And as you can see, these are identifiers mean the exact same thing. This one means this thing. These are the aliases for the byte type: signed byte, unsigned short, signed short, unsigned 32-bit, signed 32-bit, unsigned 64-bit, right here in this group. Wait, what? U pointer is 80? Is that a mistake? Okay, well, whatever. I don't think this should actually be here anymore. I'll have to investigate that. This, I think, is a leftover from earlier in development. This is also an unsigned, you know. I'm seriously, what's up with that? Hold on, I want to debug this, right? Oh, no, we need to not get distracted. Anyway, I'll investigate this later, but don't use this one. Don't use this one. Signed 64-bit. You could tell, guys, that I've been working on this so long that I've forgotten some of the things I've done, right? I don't remember whether or not this works as I originally wrote it or not, because I remember I made some changes to how this works. But anyway, here's signed 64-bit integers. Here's 32-bit floats, 64-bit floats. Here's some other keywords: break, data, string. We're going to talk about the data statement later. String, this is only used in the data statement. It doesn't define a type. End, continue, if, else, while. Go to and jump mean the same thing. Return, tail, size of, static. Yeah, static is a keyword too. It means basically the opposite of public, right? Static is implicit, right? Pub, public, struct, class, they mean the same thing. You can check these values here, right? This is in this is in parser.h, part of the Coder's Basilisk compiler. Static, size of, pub, public, struct, class, asm, method, pre-decl code gen. Yeah, and you can read, right? The ones with the same return value number have the same function, right? So you see here that all these things return 2, and that means that they mean exactly the same thing. Now, hold on. I'm actually like... pointer underscore size. It requires a... I see, so it relies on pointer underscore size. Where do I... Okay, yeah, so it looks like it does still work, upointer. Upointer is a feature that I added to the compiler a long time ago. I wonder if it works for global variables, right? Anyway, that's something to investigate another time, right? What I'm wondering here is, did I write a bug, right? Because the thing is, I'm actually not sure upointer fully works. But anyway, that's not important. Let's scooch this to the side for a moment. Another difference between Coder's Basilisk and C is the switch statement. The switch statement works differently in that it jumps to a label. And this thing here, I have an example switch statement. A switch statement accepts an expression, an integer expression, followed by a list of labels. And each of the labels can have a comma after it or cannot, right? I believe you can even have a trailing comma. I believe that's valid. Let's check that. Yeah, you can. You can have a trailing comma. And basically what it does is it just jumps to that label. Now the label has to be in the exact same scope as the switch statement. It can't be in a scope above or a scope below. And it can't obviously be in a different function or anything like that. So that's how switch case works. And the reason it's made this way, by the way, is to avoid the complexities of having to deal with calling constructors and destructors when you do a switch case. That's why it's written that way. And this is how you define a label, by the way. This is part of the difference, right? So anyway, switch case works differently. That's another difference. We're getting back on track, guys. We're not doing that. Methods for structs. This is another difference, right? So when you declare a struct, right? So that here we're declaring struct A and class bit 32-bit. Bit 32-bit is actually a union. You can see here, so it's a union. This means that it's these all occupy the exact same memory. There's going to be a demonstration of that later. We also have predecals here, but we have a constructor and destructor for bit 32, bit32.ctor and bit32.dtor, right? And you know, bit32.ctor is just clearing the object. By the way, this is an example of using cast to byte pointer this size of bit 32. This is how you use size of. Bit size of only accepts a type. It does not accept any. You know, you can put a type name in here. I could put a 1. That would be fine. You know, in fact, let's just show that. That'll work exactly the same. You know, yeah. See, and that's that, right? If I were to put something longer in here, though, that would break, right? If I put 5 in here, this could compile. It could, or it could not work, right? It looks like it worked, so we got lucky. But in general, there's no guarantee that it would work. Anyway, so that's how size of works, that stuff like that. But anyway, let's get back on track. Methods. We have methods, and I only defined constructor and destructor, right? The constructors and destructors are called automatically, right? I could show you where it's being called, right? So for instance, where do I define? Here we go. I defined bit32 variables A and B here, so they're going to be called right here. Let's print. And now let's put these in here, right? Let's put something in the this destroy. Construct. Let's see here. Right, it constructs them at the beginning of the scope. Before these H's are printed. Then right after get global PTR demo, right, we go to the end of the scope, and then these destructors are called, right? So that's how constructors and destructors work, right? Okay. They only, by the way, are ever automatically called inside of a scope. There's no automatic calls in global for global objects, right? You need to manually call those, and that's an advantage over C++, by the way. C++ will hide that control flow from you, and you have no idea what order your global constructors are called in. At least I don't think there is any standard way to know. When a switch statement works differently, methods for struct. Goto cannot jump into a scope, but can jump out. Okay, so let me show you this, right? If I let's say that I want to have an if statement run. If 0, right? Inaccessible /n, right? And let's give it a label. My label. I cannot go to my label. Won't work. Goto uses out of sequence or non-existent jump target. My label, right? See, goto cannot jump into this scope, but we can go to my label too, right? So this will work. We can jump out of this scope, So we're inside of a scope here, and we jump out, right? So and let's. Now this is accessible, Hello world. See, accessible gets called right here, and then we go to my label 2, right? And it goes here, right? In fact, we could stick this here, right, and make an infinite loop, And it'll just print accessible over and over again, right? Like this. Yeah, see, because this makes a loop, right? So that's a loop, right? And obviously, you could have a more complex condition in if you wanted to, right? I'm just showing you how the syntax works, right? So that's demonstrating to you how goto works, right? And actually, let's not have an infinite loop here. Let's actually do it by going here, right? Now, there's no void pointer or type, right? And I don't need to show, there's no way I can show this to you. There's basically all you can really know is that there is no void keyword, so there is no void type, right? Internally, there is a void type, but you can't declare variables of that type, and it's basically only used for the return value of functions to denote that it has no return value. Coder's Basilisk also has pretty strict pointer aliasing. You can't assign a byte pointer to an arbitrary thing, right? Because there is no universal pointer type. There's no void pointer, so there's no universal pointer type. That's basically the thing that you need to remember. Cast type, right? I showed that to you, right? In the constructor, right here. There's the cast keyword. So cast accepts a type, right? In this case, byte pointer, and then it's basically like it's the same thing as a C style cast. It's explicit, right? And the reason we need it is in order to be able to do this, right? If I omit the word cast here, this will stop working. See, expr parse terminal failed, right? If you omit the word cast right here, it tries to parse this as an expression node instead of a type. So you have to put in cast there, and that's how you get this, right? Yeah. And so that's why that exists. You cannot get the address of a local variable. There is no ampersand prefix, right? And I demonstrate getting the address of a struct member with .and, right? Where do I do that, though? Here, right? Okay, so let's try to get the address of a variable, right? Let's say z equals and a.I, right? Or actually, let's say it's and x. Or let's declare int www. Let's try to get the address of www, right? This won't work. Okay, is the terminal broken? Okay, the terminal fucking broke on us. That's not my software's fault. That's we're diffs from C, right? CBAS main. This, yeah, okay, there. So this will not work, right? Expr parse terminal failed. Line 239, and behold, line 239 right here. It should be where it failed. Column 7. Yes, it failed right there. So it cannot recognize this prefix ampersand, right? It doesn't exist, right? And that'll work. So anyway, that's an example of, you can't get the address of a local variable. What you can do is you can get the address of a struct member. You can also get global PTR. You can get the address of a global variable. And of course, if you've declared a local struct variable, struct variables, their name always turns into the address, right? It decays into a pointer, right? You can't get an L value struct. All right. Anyway, so where were we? Strict pointer aliasing, cannot get the address of a local variable. Right. We can get the address of a struct member with .and. So let's scroll down here. So we've declared this int pointer z, right? And we assign it to the address of A's member I. And as I recall, A is a bit 32, which, as we discussed before, is a union. So this is just going to be the address of the union, right? We assign the value -23, and then we call funky on it. Now, funky is a little funky. Right, it's a little demonstration here of how we use funky here is, along with proto here, is an example of how we do function pointers and stuff. Funky doesn't itself use funky pointers, but we can call it indirectly through proto, right? Right here, right? Call f and ptr, then we accept a prototype function, this proto here. That's saying we're going to call a function with the exact same prototype as this function here. We pass it an expression saying, an expression evaluating to a byte pointer, right? and then we pass it the arguments to the function. And then this whole node is going to evaluate to the return type of whatever this prototype is, right? Now, it's very important that you use function pointers properly, right? You can obviously mess them up, right? So always make sure that you only use valid function pointers, and you always use valid prototypes and all that, right? I know we're rambling. I'm rambling again, right? You just have to roll with the punches, guys. I'm sorry that I'm bad at explaining things, you know. You cannot get the address of a local variable. I talked about get global PTR or get fnptr, call fnptr, replaces function pointer typing. Okay, so C's function pointer system is ass, right? It's probably one of the worst parts of C. So I replaced it with get fnptr and call fnptr, and I showed it here, right? We have this byte pointer, f pointer here, and I assign it the value of the function pointer for funky, right? Funky is this function we declared up here. By the way, notice something I'm doing here, right? Bit 32 is just declared here, right? This variable here does not have an asterisk, yet it's the exact same type as this one. Similarly, the return type is the same, right? Also, you know, we tail to funky2, and if we scroll up to funky2, funky2 has an asterisk next to the to this argument, right? And we could put one here, right? If you know anything about the tail statement requires that the function you're tail calling have the exact same prototype as the function you're tail calling from. And so this is basically a sort of proof to you that this function prototype and this function prototype are identical, except, of course, that this has a different name, right? Which doesn't matter when you're tail calling, right? So, you know, that's how that works. We're going to talk about that later. I just wanted to mention that, right? So get fnptr, call fnptr. Let me talk about call fnptr again, right? Call fnptr keyword, open square bracket, then we have an identifier, the name of the function that we want to, whose prototype we want to use, right? We're going to call a function with a prototype that has call a function whose prototype is identical to this function's. Then this is an expression, right? And this expression consists entirely of f pointer, which is this local variable. F pointer is a byte pointer. And then here's the function arguments, right? You could do a, right? And if this took more arguments, you'd put them here like this, right? But this only takes one argument, so yeah, right? So this is how you use call fnptr. And I hope I don't need to explain that. Let's scroll up. What's the next thing to talk about after get fnptr? The tail statement. I already showed you guys that. The tail statement is new in Coder's Basilisk. It's an improvement over C. It allows you to manually implement a tail call optimization into your code. Now, when compiling to C, this relies on an optimizing C compiler in order to actually perform a tail call. But in general, an optimizing C compiler probably will implement this as a tail call. So, you know, it's just that when this exists as part of the language, right? In general, tail calls are always tail calls. At least they should be, right? When compiling to C in particular, it's a little bit wonky whether or not it actually will, right? But it pretty much always will, right? But when compiling, for instance, to other targets, it always should, right? The reason that I can't guarantee it when compiling to C is that C doesn't have tail calls as a built-in feature. So tail calls in Coder's Basilisk, when compiling to C, can't quite guarantee actual tail calls. But anyway, that's not here or there. Let's get back to the point. This function here tail calls this other function, funky2. If we scroll up to funky2, funky2 is defined here. Here's the arguments. There's only one argument. Returns this, right? And this prototype is exactly the same as this prototype. Now the reason, as this one, which is also the same as this one, but this is the thing we use in call fnptr, right? Now, by the way, notice here that I declared it no export. If we look in, look for proto, we're never going to find it's not there, right? But if we remove that, and then we look at auto out.c, now it will be there. Here we go, right? So here's this function that now appears, right? Because it's not no export anymore, right? Let's make it no export again, and now it'll disappear. And so this is an example, by the way, of how in practice you would actually use call fnptr. You would declare your prototype no export, right? And watch this go away. This is going to go away. Boop. See, and now it's gone, right? So anyway, that's that, right? But anyway, we were talking about tail calls. Where's funky? Where's funky? The funky function. Here's funky 2. Here's funky. Funky tail calls funky 2. Here's funky 2, and this just returns the return value, right? It returns the argument, pardon, right? So this is how you use tail calls, right? Structs are always passed by pointer. The name of a struct variable is in an expression evaluates to its pointer. Hopefully, this whole shenanigans with bit 32 star versus bit 32 no star explains this to you. But in general, anytime that we have, let's say A here, right? A is actually going to be an address, right? So let's actually print that out. Fprint r/l/int, and we're going to cast it to int. Actually, let's cast it to i64. We're going to cast a to an i64. You're going to see that this is going to be this weird long number instead of whatever the hell a was before, right? In fact, let's assign a.i a value, right? Get global PTR. So right here, this thing right here, this is now a pointer, right? If we cast it to an i32, it'll be a shorter thing, I believe. Oh no, it's here it is, right here. Yeah, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so this is a 32-bit integer now because we've cast it to a 32-bit integer. So this is a pointer being cast to a 32-bit integer, right? And then we're printing it as an int, which I'm actually not sure if /int can handle 64-bit integers. I forget how I implemented it. Oh, you know what it is? No, I actually do know. It's implemented through I2A, and I2A is defined to work on, let's look at the user group, I2A. Target IMAX. So it does work with 64-bit values, right? At least it should, right? Let's actually test this really quick right here. I just want to know, right? Just want to test this. Yeah, this is definitely more digits than can be handled by a 32-bit integer. 3, 6, 9, and then it keeps going. Right, so this is a 64-bit integer, right? Yeah. So yes, this can handle a 64-bit integer. I just wanted to test that. But anyway, let's get back to the point. We were talking about tail calls, and then we did the next thing. Structs are always passed by pointer. I demonstrated that. You cannot pass structs by value into functions. I talked about that. Anytime that you declare a function accepting a struct by value, it'll secretly turn it into a pointer. Similarly for return values, which is this point, the index operator becomes pointer addition when applied to struct star. Okay. So I don't think I have a demonstration of that. So let's say we have bit 32A and bit 32B, right? But what happens if we do of 0? What happens, right? So watch this, right? Let's highlight this. Print you're gonna okay, right? It's gonna do exactly the same thing that it did before, right? Whereas look here, bit32.I equals -23. See, right? So what this did here, right, is it the expert index here, right? This indexing expression, this pointer dereferencing operation, got turned into pointer addition. We can also do 1. This is going to access out of bounds memory. We can see what's sitting in that memory. Looks like garbage, right? So this is, when you do the indexing operator on a struct star, right? On a struct pointer, it's going to just turn it into pointer addition. This is very useful, just as a sort of nice syntax thing, right? But it also prevents you from ever accidentally dereferencing a struct pointer, right? If you have struct star, you can't dereference that. If you try to, it'll just do pointer addition. So that's that, right? What's the next major difference we need to talk about? Talked about that. The data statement. Aha! So in Coder's Basilisk, there is no array initializer stuff, right? So instead, we have the data statement. And the data statement's purpose is to basically bake a whole bunch of static data into the binary, right? You can have data type, and by the way, you must be able to declare a literal of this type, right? Int star would not work here. Int, float, char, all those work. And here's data string. This is the string keyword being used. This is the only use of the string keyword. Data type, identifier, and then the data. And here it is for int, right? This is a list of integers. In this case, 6 integers, right? Separate them into groups of 3 so you can count them very easily. And we print those out somewhere here, I believe in main. Yeah, here. See, I print out my ints of I, right? So the identifier to a data statement is going to associated with a data statement is going to turn into a pointer to a thing of the element, right? So this is int pointer, and then we index it to get an int, right? Int pointer indexed with I gives us an int, right? So this is element I, right? And you can see at the bottom of the printout, right here, it prints out these numbers. 3, 3, 4 minus 1 is 3, -5 times 10 is -50, 49 is 49. This number here is that number, and this is 37. Yeah. So that's how you do that. All right. Okay, hold on. What's the next major difference? The data statement, we talked about that. The move operator. Okay. So because structs, when you have a struct variable declared, you cannot reference it by value, right? You might wonder, well, how do I copy between structs? And the way you do it is the move operator. The move operator accepts a pointer on either side of it, right? An expression evaluating the pointer on either side, and it will take the data pointed to by this and move it to the memory pointed to by that, right? It's mem copy, basically, right? This is the mem copy operator. By the way, if these pointers overlap or if they're identical, it's invalid, right? That would be invalid. That would be undefined behavior. You're not allowed to do that. So keep that in mind when you write code. The move operator only works if the memory pointed to by the two pointers does not overlap at all. Okay, so that's this is the move operator. It obviously also works with int pointers. It works with int pointer, 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 pointer. It just removes one layer of pointerage and says, okay, I'm going to copy the memory pointed to by this to that, right? It's just mem copy, basically. That's the move operator. Static declaration by default, right? So you can see here these methods here, ctor and dtor and demo cast vec. Let's look at this function in the generated C code. See, it's declared static in the generated C code, right? And as you can see here, there is no static, right? We could add it. but it'll just compile exactly the same, right? See, it's exactly the same. So it's static by default, right? The only reason we have the static keyword, by the way, right, is so you don't accidentally do something like that. Cannot have public and static; they are opposites, right? Let's actually leave that in there for demonstration purposes, just to demonstrate that this keyword is here when you read the code. When you use static by default, that's a major difference. Static must use pub to expose symbols to other compilation units. Main must be declared pub or public. Public works. So we've declared this. If we omit the word public here, I believe it won't compile. Function pre-declaration is okay. Here. We have to change the pre-declaration to I pre-declared main. See, and the pre-declarations must match, right? See, GCC bitches at us. Undefined reference to main. See, the main function was declared static, so now GCC's linker, LD, cannot find it, right? So you must declare main public when exporting C, right? So, hopefully that illustrates that point for you. Static declaration by default must declare pub to expose to other compilation units. This also works on integer, on variables. It also works on data statements. I believe I can put that right here. And let's go to see, my ints is no longer static, right? You can see my string is static because we did not include the public keyword, but my ints is static, right? So the public keyword also works on variables and data statements, right? And by the way, you should know that data statements, when compiled to C, just compile to arrays, right? And they are mutable, by the way, when they are compiled. So they don't end up in the immutable memory of your process. That is something to note for more advanced programmers. Static by default. Pre-decl versus extern. Okay, so right here we have some pre-declared functions. You can also pre-declare variables. I did not demonstrate that here, but let's pre-decl. Yeah, see, now we're pre-declaring this cool variable. We can also pre-declare some other variables. Pre-decl. You can also pre-decl this integer. I believe this should, yeah, so anyway, we pre-declare this integer and then we use it, right? If we try to declare it public here, it'll bitch at us again. At least it should. Yeah, see? Global variable pre-declaration definition mismatch is public, right? So see, it was declared public here, but it's not public here. But we can do static. Right? This is valid because this is static implicitly. Yeah. So that's an that's a brief explanation of that. I know, guys, I'm doing a very poor job of explaining things, but again, you're gonna have to roll with the punches. If you find my explanation in this video to be confusing or hard to listen to, you can just look at the code. Size of only works on types. Okay, so basically in C, you can do, like, I could do size of I here. All right, let's try to do that. Int size of I, right? And this will not work because I is not a type. Type parsing requires a type name. See, it says that there's no type name here. Line 42, column 15, that should be right there. Yes, line 42, column 15 is right here. This is not a type name. You can do size of upward. Let's look for this text. Where is it? 8. See, so this size of upward is 8, right? You can also put an array in here. This should be 3 times 8, which is 24 if I know math. I do. I know a little bit of math, right? You can do upward pointer. Now, a pointer on this platform is exactly the same size as an upward, so it's just going to be the exact same value, right? But we can do an upward pointer. Size of an upward pointer, 8. Let's find the size of a bit 32. Should be 4, unless I fucked it up. 4, yeah, because it's a union. Yeah, so anyway, that's how you use size of. Size of only accepts a type. You can use, you can put stars and an array size in there, but you cannot put in variable names or anything like that. Pointers are only dereferenced with brackets, never asterisks. Let's quickly show you that. Okay, where do I dereference, say, a... Okay, so see here, we get global PTR of x, right? In fact, let's do something, right? Z equals get global PTR x. So now Z is an alias of x, whereas, okay, see right here, get global PTR, we assigned 2048 to x, right here, right out here. Let's try to do the C style thing, right? Star Z, this won't work. Did you forget an end somewhere? Expert parse terminal failed, right? It gives you a weird cryptic error right here, right? So star Z, you cannot do what you do in C. You have to use brackets. This will work. Now it's going to print out 3 times. Right here, yeah. Another thing that I should show you is that, okay, we talked about that. Size one. Type system is a simplification of C's type system. Okay, you have a base type. Okay, so the way that I'm explaining this, right? You have a base type here. This is a type name. Type names are always one word. There are never 2 words. There's no like long space int. That's not a thing. There's long, and then there's int, right? Which in this language happens to mean the exact same thing, but whatever, right? Actually, it does mean the same thing in C as well, doesn't it? Well, on 32-bit platforms, right? On 64-bit Linux, long is the size of a pointer, because Linux is stupid that way. But anyway, so oh yes, I should mention that long is defined as being the size. You can see these aliases, right? So if we go to the list of int aliases, long is an alias for int, which is an alias for i32. So this is a signed 32-bit integer. Similarly, if we go to unsigned 32-bit integer, ulong, there is no unsigned space long, there is no unsigned space int, there is uint, there is ulong, right? We also don't have the word unsigned. In C, you can do unsigned. This is a type all by itself. It's an unsigned int. But in Coder's Basilisk, it is not so. But this is the general form of a type declarator, right? Base type, some number of asterisks, could be 0, could be 12, could be 100. Open square bracket, constant integer expression, close square bracket, right? And you can omit this if you want, right? Obviously, right? So this, for instance, is another type declarator, float, right? This is a base type. There is 0 asterisks and there's 0. There are 0. There's 0 asterisks and there's no array length, right? The array length is 0. That's actually how it's stored internally, right? In fact, I can show you that that's invalid, right? Array length of 0 is invalid. Array must be of greater than 0 length, right? And the reason that is, by the way, that is a feature that is missing from C. You cannot have a 0 length array at the end of a struct to indicate that it can be longer than that, right? C has that feature, right? You can declare a 0 length array at the very end. Coder's Basilisk does not have that. Records are always the same size in Coder's Basilisk. That is another difference from C I did not have in this list. Let me add that. 30, no end of structs. Okay. So this is not a thing, right? You could do of 1. That would be valid, right? And then you could have the, but then copying the struct wouldn't work properly, right? It wouldn't copy beyond the first element. So no array of 0, right? That's a feature, right? Okay, so let's get back to where we were. So I already explained this. No multi-dimensional arrays. Okay, so let's try to declare this variable here, right? My cool variable 2, right? We're trying to declare a 2-dimensional array of, let's say, just flat integers, right? Identifier required in global variable declaration. Aha. Call line 91, column 7, which should be right there. Yes, see, it expected an identifier right here, but instead it found this crap. So multi-dimensional arrays are not allowed. No multi-dimensional arrays, right? If you want to do a multi-dimensional array, just multiply the dimensions together and make a single-dimensional array, and then index it with y times width plus x or something like that, and then z times width times height. Right. So just extend this format here for as many dimensions as you need, right? Where width and height are constants. You replace these with integer values. Right? This is how you would index it, right? Yeah, so I just need to explain no multi-dimensional arrays. That greatly simplifies the type system, by the way. You cannot insert nulls into string literals. Right? So if I do \0 here, this will not produce the result you might expect. Let's scroll up here. A string 0 literal. See, there is no null here, right? If this worked the way that you might expect, then this would be replaced by a null character. That's how it would work in C, and then the rest of this would not print. But Coder's Basilisk does not allow you to put null characters in the middle of a string because it's kind of nonsense. In fact, let's actually keep that for demonstration purposes because I want to put that in the repository. Pointers do not automatically decay to integers for Boolean ops, such as not. Okay, so the reason that this is important, right, is you see the z pointer here, right? We can do if. Let's try this, right? I believe this should work. Works. I actually don't remember. I think it does. Yeah, see, but let's try not see. This will give us a compiler error. Aha, pointer math is limited to addition, subtraction, assignment, moving, casting, equality comparison, and indexing. So we have to do z not equal to 0. Or, well, actually, right, in order to get not z, we do z equals 0. And notice here that we're allowed to compare with an integer here, right? We could also compare with 12, right? This is totally valid. I believe it also works with const. By the way, yes, this is a thing in Coder's Basilisk, right? So we can const x per I. This is a valid thing in Coder's Basilisk. This is a special keyword. There's also const x per f. This will give us compiler error. Incompatible types. LSIM and float, right? See, so line 256, column 3. And this, by the way, when it prints out errors in the code from the code validator, it'll often print out the start of the statement and not the start of the expression. That's something you need to be careful of. So you can't compare a pointer to a float, right? So I can't, 12.3. This will not compile either. But I believe this will work. Does it? Does it? No, it does not. Okay, it does not. I did not remember that. You cannot compare to an integer expression. You must compare to a static integer. So incidentally, I believe this means if we declare q I believe, I just want to show you guys this. Q equals 0. If you compare Z to Q, remember Z is this integer pointer. See, it does not work here, right? So in order to compare a pointer with an integer, it must be a constant integer expression or an integer literal. Let's change this to not equal so that it prints. Because I want it to print in the demo. Works here, right here, right. Scroll to the top. Where were we? Right. Pointers do not automatically decay to integers for Boolean ops, such as not. Right. I just demonstrated that. No comma operator. Okay. So let me quickly explain this. Right. Q equals 0, 1. In C, this would assign the value 1 to the integer Q. Requires a semicolon, right? It expected a semicolon here, but instead it found a comma, right? Comma is not a valid operator, so that's that, right? Incidentally, okay, hold on. Incidentally, no comma operator, comma and semicolon are equally valid to separate expressions in for. Look at the for loops in this thing, right? This one uses semicolons. Let's find another for loop in here. This one uses a comma and a semicolon. Comma for the first one, semicolon for the second one. This one uses a comma and a comma. Where else do I use for loops? For loop here. Well, you know, I could put a comma here, right? So this will work. Yeah, so you can see that you can use commas or semicolons to separate the terms of a for statement, right? To separate the expressions. Oh, by the way, you can't. I couldn't like do this. This is not valid, right? This is not valid. You can't do this. We do things like C89. You can't declare a variable there. Yeah, so you can't declare a variable here, that's of note. But basically, as I was mentioning, no comma operator, comma and semicolon work to separate expressions in a for in the header of a for statement, right? That's where we were at. There is no ternary operator, okay? So this is pretty simple. The ternary operator is that thing with the question mark and the colon. Let's scroll down. Let's say I equals 3 question mark, which should turn out to true, and assign it the value 4, 5. 3 is positive, so it should, if this was C, assign it the value 4. But this is not C, so the question mark gets turned into an error. Column 7, which is right here, line 314, column 7. Right. So there is no ternary operator. Scroll down. Function calls with no arguments and method calls can omit parentheses. Same for declarations. You can see here that sometimes when I declare methods, with these two methods, omit parentheses. Let's add parentheses here. This will still work. All right. And then when I call a constructor or destructor, right? When I call functions, right, I can call them that take no arguments. Hold on. When I call basic syntax showcase here, I omit the parentheses here, right? So let's add parentheses. This will still work. And let's omit basic syntax showcase so to show you what it would look like if it was not there. It would be a lot shorter. So it's clearly working. It's clearly running. So anyway, and that's that, right? So you can omit parentheses from method and from method calls. Also, somewhere here, I do a demonstration of calling a constructor. Demo cast vec. Yeah, see, I call the ctor here somewhere. Yeah, here. I call .ctor right here with no parentheses. And I could add the parentheses if I wanted to. This would work exactly the same. Now, incidentally, because vector is 0 initialized, this actually happens to be the correct initialization. It's already constructed by default, right? So this CTOR, I actually don't need to call it. It doesn't actually do very much for the program. But, you know, it's for demonstration purposes. I just need to show you this is valid syntax, right? This is valid syntax for calling a method with no arguments, right? And so is this. I can call it with, I can use parentheses, or I can not. Similarly, if I have a function that takes 0 arguments, I can have parentheses, I can not. By the way, I should note that unlike C, there is no, you can't do void, right? This is not a thing. Void is not a keyword in Coder's Basilisk, so this declaration does not, this declaration form does not exist. There are no, there's no like, I forget what it's called, these kinds of functions in Coder's Basilisk. You can't have ... Printf, for example, is one of these functions. I forget what they're called. But in C, there are functions that have this kind of functionality. That have an argument list. And there's this whole complicated thing where you like get arguments in the argument list in C. It's really complicated, but all you need to know is that does not exist in Coder's Basilisk, right? So there's none of that. I'll add that to the list. One. No var args. I remember now what it was called. No var args, right? No return operator, function calls with no arguments, methods calls can omit parentheses, same for declarations. Local variables exist for the entire duration of their parent scope and can therefore be used anywhere, even before their declaration. Okay, so let's scroll down here. I already showed this to you. But these variables are declared down here at the bottom of this scope, if 1 not equal to -1, right here. This if statement creates a scope right here, and then we can use these variables anywhere here, right? We cannot, however, use it right here. This should get the compiler error. Unknown identifier A on line 229. See here, right? But it's valid here because this variable exists in this scope. So, and you know, I have a comment here, variables declared like this should explain it to you. Char is unsigned, alias for byte. Okay, so this is a pretty obvious one. So you see here, main is declared with schar instead of char, right? And the reason that this is done is because in C, char is defaulted to signed on most platforms, including the one I'm currently on. So we have to declare schar here. In the compiled C code, I showed this in another tutorial. Let's go down to the main function. Where's the main function? The main function, where is the main function? Method. Where's the main function? Aha, here's the main function, which, by the way, you should note is not mangled. The main function is special in Coder's Basilisk. Main's name will never be mangled. This comes out as char in C, but here it's schar, and that's because char is signed in C, but not signed in Coder's Basilisk on most platforms. Some platforms, C has signed char, and you can change the C code generator for that target if you need it. Function arguments must have the same names in their pre-declaration as in the declaration proper. Okay. So you see here how we pre-declare main. Let's try modifying it. This will give us an error. Argument name mismatch, line 310. Right, so we pre-declared it here, and then if we go to line 310, which actually it points us right here. On the previous line, it says, right here. This argument here does not have the same name as in the pre-declaration. So it must have the same, by the way, you can also pre-declare multiple times. That's totally valid. You know, I can pre-declare this as many times as I want, as many aliases I want. but the names of the variables must be the same, right? And it must have the same return value. Long, we can have, hold on, what are some aliases here? Sint. All of these are valid. But if we change the name of any of them, it's suddenly not valid. And the reason this was done in Carter's Basilisk, the reason I enforce that the argument names be the same, is that I want to make sure that when people have header files with their list of functions to ship libraries, that these variables have sensible names in the header files, right? Because I don't want you to give them stupid names. All right, so that's that, right? And obviously you can pre-declare multiple times. That's true in C2. Chunder is unsigned for alias for byte. Function arguments must have the same names in pre-declarations. This is signed. This is arithmetic right shift. Signed arithmetic right shift. Okay, so let's look at that. Right, I have a demo for bit shifting somewhere here. Aha, here's the bit shifting demo. Okay. If we look right here, here's -173 right shifted by 2. Let's see what that does. It'll print out nonsense, right? Right here, nonsense. Right shifted by 2 with arithmetic, -44, which is the division by 4, right? We can actually demonstrate that. Well, I mean, like, you know, it's because of the differences in how bit shifting works versus division. It's not exactly the same, but you know, this one is -44. This one is -43. You know, these two, right? Then we have this, right? (43, 43, 43), right, for these two, these, right? These do the exact same thing. This one and this one are the two things you need to pay attention to. This is logical shift right. This is arithmetic shift right. For unsigned integers, they mean the exact same thing. But for signed integers, i.e. negative numbers, they do two different things. Incidentally, you can do this on an unsigned integer. It's just, you know, why would you want to do that? Anyway, so that's that. That's what you need to understand. Arithmetic right shift is a different operator from right shift. This is, I think, is an improvement over C because you can always tell just from reading the code whether or not an arithmetic right shift or a right shift is happening without trying to figure out what types are involved. It's clear just from the operator. Stir X, stir nec, and impl stir X. Okay, this will take a while to explain. But Coder's Basilisk has an operator for null terminated string comparison. So here we stirred up some strings, right? And we do some comparisons, right? Where is this printed out? After the bit shifting demo. Right here, 0, 1, 0, right? This one, stir X. This one, no, that's false. 1 is not the same. Stir 1 is not the same as stir 3. Stir 1 is the same as stir 2. They contain the same code, right? It is two different allocations though, so they're not the same pointer. It's comparing the contents of the string. Stir 1 does equal stir 2, so this turns out to be 0 because this is stir nec, right? Now, in order to use stir ec in non-cogen code, you need to define it somewhere, right? You need to define this function somewhere. Impl underscore stir ec, this function here. This tells the code generator what to do in order to generate these, to have the stir ec operator work, right? And this is necessary just so that code generator authors do not have to implement stir ec and stir nec in their code generators, right? I don't want to put that burden on code generator authors. So you have to implement stir ec in your code. Impl stir ec somewhere. You must implement this function in order to use this operator. So that's that. That's the new thing. No array 0 of n struct. We already talked about that. All functions have a static constant number of arguments, no var. We already talked about that. Anyway, so that's all the differences. Now I'm going to I'm going to push this to git init, dot, commit, dash, hold on. Git branch dash m main, git commit dash m init, add origin. We need to create the repository. Yeah, I'm watching an anime. I was watching an anime and I interrupted it for you guys. Oh, this is YouTube. I don't want to go to YouTube. Let's go here. New repository. CBAS tutorial for diffs from C. Create repository. Git at codeberg.org:gex/this. Wait, what? Remote origin already exists. Oh, weird. Oh, okay. Okay, here we go. Okay. Oh, you know what it is? I copied the folder. Okay, hold on. We wrote this command before. This should work. Here we go, right? And here's this. So it's here we go. Now the license file is in there, so now you have this available to you. Here, hold on, let's go back to the code. Right, now that you have the license. So you should be able to see this, repository should be linked in the description, and you should be able to click on it, hopefully. I don't know if YouTube will let me paste a link in there clickable. I think it has been letting me do that recently, but you know, in essence, you'll be able to get this to this repository, and you'll be able to access the code if you want. I know that this tutorial has been very rambly and very distracting. Oh yes. And before I go, we've been rambling and distracted enough that, you know, if I ramble and distract a little bit more, you guys won't mind. What I want to know is, okay. Where is pointer underscore size set? You know what it is? Pointer underscore size is probably defined here. Yeah, so pointer underscore size is defined as 8. So it does work. uPointer does work. Okay. uPointer is defined as being the size of a pointer on the host. So it's always defined as 8. Yeah, so anyway, CBAS was never implemented 32-bit, so this never actually happens. In fact, I can remove that. Or I could just leave it the same. And so I just wanted to check this. So uPointer does work. Okay, whatever, right? Anyway, that's the end of the video. I hope you guys enjoyed. Thanks for watching.